Have you ever thought about how engineers determine the deflection of beams in existing buildings or structures? Salutations! We are Group 2 from AR-301 and our topic is the deflection of beams.
Beams support loads across various structures, so it's crucial for engineers to predict how much a beam will deflect under these loads. Excessive deflection can damage other parts of the structure, make it feel unsafe or hinder its intended use, even if the stresses in the beams are low.
Construction codes typically specify the maximum allowable deflection, leaving engineers to calculate how much a beam will actually deflect.
There are several methods for this calculation, and in this video, we'll focus on double integration method and Macaulay method.
Both methods rely on assumption of small deflection and stresses remaining within the elastic region. Therefore, the deformed shape of the beams is referred to as the elastic curve. We can denote x as the distance along the beam's axis and y as the vertical deflection. Our goal is to determine how y changes along the length of the beam while assuming there's no displacement along the x-axis. We're also interested in the beam's angle of rotation, theta. The beam's slope can be deformed as dy over dx. Given our focus on small deflections, we can use the small angle approximation, meaning the angle of rotation equals the slope. In essence, the angle of rotation is the first derivative of y with respect to x.
To understand beam deflection under load, we can look at the moment curvature equation. This equation allows us to calculate a beam's curvature based on a bending moment. Here, m represents the bending moment, r the radius of curvature, and ei the flexural rigidity of the beam, indicating how resistant it is to bending. The term 1 over r denotes the beam's curvature. The moment's curvature equation is the first step in calculating beam deflection, as it provides insight into how the beam will deform under a bending moment. There is a mathematical equation that relates curvature at any point on a curve, which we can combine with the moment curvature equation to link beam deflection with bending moment.
However, this equation can be complex, so let's simplify it. By assuming elastic deformation and small slopes, we can disregard the squared dy over dx term, yielding a simpler differential equation for beam deflection. We can find an expression for deflection by integrating this equation twice, known as double integration method. It's easier to grasp this method with an example. Consider a cantilever beam with a load applied at the end. Begin with the free body diagram to determine the reaction forces. Next, we calculate the bending moment along the beam by analyzing a slice of the beam. We find that the bending moment increases linearly with distance from the concentrated force P, giving us m is equal to negative px. We can substitute this expression for m into the deflection differential equation and apply double integration method to determine the beam's deflection.
Since e and r are constant, we can factor them out of the integral and integrate the moment equation with respect to x. Remember to include a constant of integration which we'll call c1. After a second integration, we introduce another constant, leading to an equation for the beam's deflection y. We now have two unknown constants which we can resolve using boundary conditions. At the fixed end, the beam cannot rotate, so dy over dx equals 0, allowing us to calculate C1. At the same point, the deflection y is also 0, giving us C2. Thus, we've determined the deflection curve for the beam with the maximum deflection occurring at its free end. In cases where the maximum deflection location is less obvious, such as with a simply supported beam, we note that the slope will be 0 at the point of maximum deflection, setting the slope equation to 0, allowing us to find the location of Ymax. Boundary conditions are crucial for applying the double integration method. At a fixed support, with both displacement and slope must be 0, while at a pinned or roller supports, only displacements applies, allowing for a non-zero slope.
The double integration method is straightforward, but even for simple configurations, the bending moment may not be expressed with a single equation along the entire beam length. In such cases, we need to divide the beam into sections and determine separate bending moment expressions for each. After applying the double integration method to each section, we will have several constants of integrations by applying boundary conditions to support. We can determine some constants. The continuity condition between section also comes into play, as displacement and slope must match at the section. Transitions leading a system of equations to solve for remaining constants.
Dividing the beam into sections and solving these equations can complicate deflection calculations, especially for beams with many sections. Fortunately, a powerful mathematical approach allows us to define a bending moment profile with a singular expression, simplifying the double integration method. This involves using singularity functions, which are defined with special notation and follow specific rules. The input is positive, the output is the expression itself. If negative, the output is 0. These Macaulay brackets simplify the deflection calculations as they let us turn off different terms in bending moment equation as we move along the beam. Let's apply this to our earlier cantilever beam example. With a single expression for M, we can directly apply the double integration method without sectioning the beam, although using Macaulay's method streamlines the process. The double integration method can still be time-consuming to implement.